The map of the solar system you grew up with ends at Neptune, and that tidy ending is the most misleading thing about it. The planets you can name are the innermost sliver of the Sun's territory, the warm core of something that reaches outward for more than 1,000 times the distance to that last familiar dot. Almost everything that belongs to our star sits far past the edge of any poster, in a cold so vast that even light needs more than a year to cross it, and we have never once traveled out to meet it. Tonight we are going to walk all the way to the real edge of home. How far does the Sun actually reach before the galaxy takes over? Pull up that map again in your mind. The Sun in the corner, the planets strung out in a neat line, and then a clean edge somewhere past Neptune where the page simply stops. It looks finished, like the whole thing. You probably learned it before you learned to read a clock, this picture of where you live, and nothing has come along since to replace it. And for almost all of human history, that edge was not a choice. It was the honest limit of what anyone could know. The planets are bright. They catch sunlight and throw it back at us, and people have watched them move against the stars for thousands of years. Past Neptune, there was nothing to watch, so the map ended where the watching ended. The strange part is that we kept drawing it that way long after we knew better. Not out of laziness, and not because anyone forgot. We keep drawing the small map because the rest of it cannot really be drawn. The planets are close enough and bright enough to hold a place on a page. What lies beyond them is dark ice, scattered so thinly across so much space that no telescope has ever taken its picture. You cannot put a dot on a map for something no one has ever seen, so the map shows the part that catches light and quietly leaves off the part that does not. Which means the thing hanging in classrooms was never really a map of the solar system. It is a map of the lit part. And the lit part is small in a way that is hard to feel until you measure it. Sunlight reaches Neptune in about 4 hours. That is the far edge of the bright world. 4 hours of light from the center. The true outer boundary of the Sun's territory is so distant that the same sunlight, moving at the only speed nothing can beat, takes around a year and a half to arrive. 4 hours against a year and a half. The planets we know are not the solar system. They are an ember still glowing at the center of a theater so large the light barely reaches the back wall. Hold on to that ember for a moment, because the image is doing real work. An ember is not the edge of the fire. It is the last bright thing before the dark, and the dark around it belongs to the same fire, just cooled past the point where it gives off light. Much of that frozen outer material formed from the same cloud of gas and dust that built the planets 4.5 billion years ago, then got flung outward and left to freeze, though that turns out not to be the whole story. The planets are the ember. Everything past them still belongs to the Sun. It has simply gone quiet. You might reasonably stop me here. If none of it can be seen, if no telescope has ever caught it, how does anyone know it is out there at all? The answer is that we do not see the place. We see what falls out of it. Every so often, a comet drops into the inner system on a long, looping path, arriving from no particular direction, sometimes from far above the flat plane the planets travel in, sometimes from below. Some of them take so long to finish a single orbit that the last time one passed, no humans existed to watch it, and the next pass will come long after we are gone. A few scattered visitors could be chance. The pattern of them, coming from every direction at once, only makes sense if they are falling inward from an enormous shell of material wrapped all the way around the Sun. We are not looking at the cloud. We are reading its handwriting in the few letters it bothers to send. It helps to picture standing inside it, though the picture is humbling. The material out there is spread so thin that if you were set down in the middle of it, you might not have a single icy body close enough to see. Your nearest neighbor could be tens of millions of miles away, a dark mountain you would never notice was there. And the Sun, the anchor of everything we are talking about, would not look like a sun from that distance. It would be a single bright point in a black sky, the brightest star you could find, but a star all the same. Out near the true edge, it would not even be that. It would be one more light among the rest. That is how far the sun's own country reaches. Far enough that the sun stops looking like the center of anything. The first people to take that reach seriously did it with pencil and paper. In 1932, an Estonian astronomer named Ernst Öpik worked out that the long-period comets had to be coming from somewhere far past the planets and resting there between visits. Almost 20 years later, in 1950, a Dutch astronomer named Jan Hendrik Oort took the orbits of the comets that had actually been recorded and showed the same thing in numbers. What caught his eye was a quiet detail in the data. The comets that swing in from the farthest distances tend to arrive looking fresh, full of ice that has never been cooked by the sun before, as if each one were making its first trip in. That only works if they have been kept somewhere cold and far for the entire age of the solar system. Neither man ever saw the cloud. They reasoned an entire region of the solar system into existence, thousands of times wider than everything on the poster, from the paths of a few falling pieces of ice. I want to be honest about something here. Even after you have heard the numbers, they tend to stay as numbers. You can say the words 4 hours of light against a year and a half, and the meaning slides past without ever turning into a picture. And still, when I close my eyes and try to picture the solar system, the small map is what shows up. The planets in their line, the clean edge past Neptune. The instinct is older and louder than the number. It is a little unsettling to notice how much of what you call home is a place your own mind refuses to picture, only because nothing has ever given you something to see. That is the quiet thing underneath all of this. We have spent our whole lives standing in the lit middle of a room, calling the lit middle the whole house, because the walls are too far and too dark to make out. The planets are not the building. They are the lamp, and the room around the lamp is larger than the lamp by a margin that will not fit inside a human head. So, if the bright planets are only the ember, and the real territory runs out into the cold for thousands of times farther than the page admits, then a simple question starts to press. The edge has to be somewhere. What actually decides where it is? Where does the sun stop being the thing in charge, and the rest of the galaxy take over? Start with the word itself, belong. To belong to the sun is not about light, and it is not about warmth, because both of those run out fast. It is about gravity. The sun owns whatever it can keep on a leash, whatever circles back instead of wandering off into the dark. A planet belongs because the sun's pull bends its straight-line motion into a closed loop, over and over, for billions of years. Cut that pull for a single second, and the planets would not slow or fall. They would simply stop turning and fly off in straight lines, each heading wherever it was already going, and not one of them would belong to anything anymore. So, the question of the edge is really a question about distance and grip. How far out can the sun still hold on? Here is the trouble with answering that. Gravity never stops. It weakens with distance, fading as the square of how far you travel, so doubling the gap quarters the pull, but it never drops all the way to nothing. By that strict reading, the sun's gravity touches the whole galaxy, the far side of it, even other galaxies, faintly, forever. If reach were the test, the sun would own everything, which is the same as owning nothing in particular. So reach is the wrong test. Belonging is not about whether the sun's pull arrives somewhere. It is about whether the sun's pull is the strongest one arriving. An object belongs to the sun when the sun tugs on it harder than anything else in the universe does, and the moment something else starts to win, it stops being ours. That one shift, from how far the pull reaches to where the pull still wins, is what turns an impossible question into a findable one, and the thing competing for those distant objects is not another planet or even another star. It is the whole Milky Way at once. Spread around us in every direction are a few 100 billion stars, along with a great deal of unseen mass we can feel but never see, and together they pull on the outskirts of the sun's territory as a single smooth tide. Near the planets, that galactic pull is nothing you would ever notice. The sun dominates completely. Astronomers call that distant pull the galactic tide, and it works the way the word suggests. It does not tug everything the same way. It stretches, pulling a little harder on the far side of the sun's domain than on the near side. And that small difference is enough to peel away whatever is only loosely held. The cleanest way to feel where that happens is to think about a small radio station. Drive away from the tower and the music does not cut off at a fence. It thins. Static creeps in at the edges. The voice gets harder to pull out of the noise. And at some point, you cannot really say you are still hearing that station rather than the hiss of everything else on the dial. There is no line painted on the road where it ends. There is only the place where its signal stops being the loudest thing. The sun's gravity behaves the same way. It does not stop at a wall. It fades, mile after mile, until the steady background pull of the galaxy is simply louder, and from that point on, whatever sits there is being held by the galaxy more than by us. You can find that place with arithmetic, which is part of why we trust it is there. Write down the sun's pull on some distant object. Write down the galaxy's pull across the same patch of space. Near the planets, the sun's number is overwhelmingly larger. Walk the object outward and the sun's number shrinks fast while the galaxy's barely changes. And the spot where the two numbers finally match is the true boundary of the sun's reach. It is not a guess. It is a place where one column of figures at last overtakes the other. That crossover sits a long way out. The planet's end, in any familiar sense, around Neptune, 4 light hours from the sun. The place where the sun loses the tug-of-war lies somewhere between 1 and 2 light years away. To set those side by side, the nearest star to the sun, the next campfire over, is a little more than 4 light years off. 1 light year is about 63,000 times the distance from here to the sun, so the sun's grip holds firm across the planets, then stretches on for tens of thousands of times that planetary span, reaching a sizable fraction of the way to its closest neighbor, somewhere between a third and a half, before it finally gives out. There is something I keep turning over about this, and I don't think it fully settles. We are used to home having an edge you could stand on, a property line, a coastline, a wall. What the physics offers instead is a slow handover. Nothing out there stops belonging to the sun on a particular day at a particular place. It just gradually belongs more to the galaxy than to us, the way warmth leaves a room without there being any single moment you could point to and call the end of warm. Knowing the mechanism does not quite give the mind the line it keeps reaching for. The edge is real, and the edge is also a fade, and both of those are true at the same time. This changes what we are even looking for. We are not hunting for a border somewhere in the dark. We are looking for a region where ownership thins toward even. Everything past the planets, all that frozen material, sits inside that thinning. The closer to the sun, the more firmly held. The farther out, the lighter the leash, until it is barely a leash at all and a passing star, or the galaxy's own tide, can lift something away with almost no effort. There is a clue in that worth carrying forward. The most distant things the sun owns are the things it owns most weakly. So we have a shape for the answer now. Not a line, a gradient, running from a tight grip near the planets out to a near whisper 1 or 2 light years away. But a gradient across what? Knowing the edge fades tells you nothing about how much space the fading covers, or what it would take to move through it. How far is it, measured in something a body could feel, from the warm middle to the cold limit of everything the sun can hold? To cross that distance, we need a ruler, and the usual ones fall apart. Miles, kilometers. The numbers swell until they stop meaning anything, because a long string of zeros is not a distance the mind can hold. So reach for the fastest thing that exists, and measure the territory by how long that thing takes to get across it. Light. Nothing in the universe moves faster, which makes it the one ruler that can't be cheated. It also means light is the measure we never have to second guess. Whatever it tells us about a distance is the floor, the best case, the shortest any crossing could ever be. If light is slow to cross something, then nothing we could ever build would be quick. Calibrate it first on distances you already carry. Light leaving the sun reaches your eyes in about 8 minutes, so the sunlight on the back of your hand right now left its source before you sat down. Push out to Neptune, the last of the bright planets, and that same light needs about 4 hours. 8 minutes to us, 4 hours to the far edge of the world we put on the map. Those are the tick marks. Hold them, because the next mark is going to look wrong. Light from the sun does not reach the outer boundary of the sun's territory in minutes, or hours, or days. It takes more than a year, out toward the far limit, 2 years or more. Picture light setting out from the sun on the day a child is born, moving the whole time at the only speed nothing can beat, never slowing, never resting. That child would learn to walk, learn to talk, have a first birthday and start on a second, and the light would still be traveling, still short of the edge of the very system it began in. 8 minutes to reach us, 2 years to reach the fence. That is not poetry doing the work. It is the same light, obeying the same fixed speed it obeys everywhere. Given a distance long enough to show how large the sun's true holdings are. A light year is still a slippery thing to feel, so let me trade it for a speed your body knows. Forget light. Put yourself on a passenger jet at cruising speed, around 500 or 600 miles an hour, the fastest most people ever travel. Point it straight out from the sun and never land, to reach the outer edge of the sun's territory, the place where its grip finally evens out with the galaxy. That jet would need to fly for roughly 2 million years. Our own species, people more or less like us, has been around for something like 300,000 years. A jet that took off before there were any humans to board it, that had been flying without pause through every era of our entire history, would still not have arrived. It would not be close. Come back to light for a moment, because something about it is worth saying plainly. Light crosses from the sun to the earth in the time it takes coffee to cool. It can lap the whole planet 7 times in a single second. By any measure we have, it is the quickest thing there is. And this distance takes it more than a year. The fastest thing in existence becomes a slow traveler out here. We went looking for a ruler big enough to make the edge feel manageable. Picked the fastest thing the universe allows, and the distance answered by making even that look patient. The ruler did not shrink the territory. The territory stretched the ruler. It is fair to ask what is really out there across all that room. The plain answer is mostly nothing, and that nothing is the point. The icy bodies are real, but they are flung so far apart that the space between them dwarfs the bodies themselves. Out in the real region, a typical chunk of ice may sit tens of millions of miles from its nearest companion, far enough that a comet could drift for its whole existence and never once pass close to another. If you shrank the region until the distance from the sun to Neptune fit on your desk, the outer edge would still lie somewhere past the end of your street, and the comets scattered through it would be smaller than specks of dust, separated by entire empty rooms. That emptiness is not a flaw in the territory. It is most of what the territory is. I notice that we keep building new rulers for this. Miles, then light, then a lifetime of flying, and none of them quite closes the gap between knowing the number and feeling it. That is not a failure of the numbers. The numbers are exact. It is that the distance was never built to fit inside a head that evolved to judge how far it is to the next tree or the far side of a valley. The reaching is the most human thing in this whole story. We stand at the lit center and keep inventing longer and longer measuring sticks for the dark, not because any of them will ever feel like enough, but because the alternative is to stop asking how far. Put it all together and the territory looks like this now. A grip that fades across a gradient, stretched over a distance so wide that light grows patient crossing it, filled almost entirely with empty space and a thin haze of frozen, drifting things. It is a fair picture, and for a long time it was the only picture anyone had. But scattered things do not always stay scattered, and the same forces that fling material outward can also arrange it. What if the cloud out there is not shapeless at all? What if it has a form? It does. Not a perfect geometric form, nothing you could name with a single word. But the cloud beyond the planets is not the featureless haze most descriptions make it sound like. It has regions of greater and lesser density. It has preferred orientations. And the thing that gave it those preferences is not the sun. The first clue came from thinking carefully about distance. Not all of the cloud sits at the same remove. The outer shell, the part farthest from the sun, stretches from roughly 20,000 out to 100,000 astronomical units or beyond, each unit being the distance from here to the sun. Neptune, the last planet we mapped, orbits at about 30 of those units. So the outer shell begins roughly 700 times farther out than Neptune, and it is thin, material spread across such enormous volume that the density is vanishingly low. Closer in, between about 2,000 and 20,000 astronomical units, sits a second region, denser and more compact, sometimes called the Hills Cloud, after an astronomer named Jack Hills, who argued in the early 1980s that it had to exist. This inner reservoir is thought to hold considerably more material than the outer shell, perhaps many times more, packed into a smaller volume. Most of the comets that eventually fall inward toward the sun may begin their journey here, rather than from the far edge. The question is whether that inner reservoir just sits there as a smooth, even shell, or whether it carries structure. We cannot photograph it. No telescope has the sensitivity to pick out individual objects at thousands of astronomical units, small and dark and cold as they are. But we can do something else. We can build the cloud inside a computer, feed in the sun's gravity, the scattering kicks from the giant planets during the solar system's chaotic youth, and the steady tidal pull of the Milky Way. Then let the simulation run forward for 4.5 billion years and watch where the material ends up. You might expect the result to look like a fog, material thinning evenly in all directions the way smoke spreads in still air. It does not. What comes out is lumpy. It has bands of higher concentration and valleys of near emptiness between them. The shape is not random, it is patterned. The pattern follows the galaxy. The Milky Way's gravitational pull does not arrive evenly from all directions. The galaxy is a disk, and that disk has a definite plane, and the strongest component of the tidal force acts along the axis perpendicular to that plane, pressing and stretching the distribution of material in a way that leaves a preferred orientation. In some simulations, the inner cloud develops arms or bands of higher density, spiraling gently, aligned not with the sun's equator or the flat plane the planets orbit in, but with the geometry of the galaxy itself. The sun may have scattered that material outward. The galaxy decided how it would settle. Think of pressing your thumb into soft clay. The shape of the dent does not depend on the clay. It depends on the thumb. The ridges, the depth, the curve of the impression all carry information about what did the pressing, not what got pressed. Now pull your thumb away and hand the clay to someone who has never seen the thumb. They could reconstruct its shape just from reading the dent. The inner cloud works the same way. The icy bodies were flung outward by the planets, but the arrangement they fell into was sculpted by the galaxy's tidal field. The orientation of the structure tells you which direction the galactic plane lies. The density pattern tells you how strong the tide is at that distance. The cloud is a dent, and the galaxy is the thumb, and the impression has been sitting there, quietly holding its shape, for billions of years. How long that shape has lasted depends on how steady the forces are. The galactic tide itself barely changes over the timescales we are talking about. The sun orbits the center of the Milky Way once every 230 million years or so. The last time it completed a full orbit, the earliest dinosaurs were just appearing. As the sun drifts through slightly different neighborhoods of the galaxy, the tide shifts, but slowly. The general orientation of the inner cloud structure has probably persisted in a recognizable form for a very long time, evolving gradually rather than flipping from one shape to another. What disrupts it, when disruption comes, is not the tide changing, it is something passing through. A star drifting too close, or a massive cloud of interstellar gas sweeping by, can stir the arrangement and scatter the pattern. But the tide reasserts itself, pressing the material back toward its preferred geometry, the way water in a bowl returns to level after you tap the side. What stays with me about this, and what I did not expect the first time I worked through it carefully, is the direction of the imprint. We talk about the solar system as the sun's territory, the sun's creation, and in the warm middle that is true. The planets answer to the sun and to nothing else you could measure. But step past them into the cold reservoir, and the arrangement of material is not oriented to the sun at all. It is oriented to the Milky Way. The galaxy reached into the sun's own backyard and left its geometry in the layout of the ice. Not violently, not as an invader. Quietly, the way a current shapes a sandbar without breaking it, the sun scattered the material. The galaxy organized it. That organizing is a clue to something deeper. The inner cloud did not arrange itself. Something reached across thousands of astronomical units and imposed a pattern. And the force that did the reaching is the same galactic tide we named 2 acts worth of thinking ago. The slow differential pull of 100 billion stars and all the unseen mass between them, working as one. The galaxy's influence does not begin at the boundary where the sun's grip gives out. It reaches well inside it, weaker than the sun's pull, but persistent enough over billions of years to rearrange what the sun alone would have left in disorder. If the tide can sculpt the arrangement of material this deep inside the sun's territory, where the sun still clearly dominates, then a question follows that will not wait. What is the tide doing farther out, where the sun's hold is weaker? What happens when it stops shaping and starts pulling things loose? We have named it twice now, without really opening it up. The galactic tide. It sounds like a metaphor, something borrowed from the ocean to dress up a gravitational concept. It is not. It is a real mechanical force with a specific way of working, and it is responsible for most of the comets that have ever entered the inner solar system. To understand the edge, you have to understand the tide, and to understand the tide, you have to let go of the idea that gravity pulls in one direction. Start with the version you already know. The moon pulls on the Earth, and the Earth's oceans respond by rising. But the rise is not because the moon is pulling the water upward. It is because the moon pulls harder on the water nearest to it than on the center of the Earth, and harder on the center of the Earth than on the water farthest away. That difference in pull across the width of the Earth is what a tide is. It is not a single tug, it is a gradient. A difference in pull from one side of a thing to the other, and that difference stretches whatever it acts on. The ocean bulges on both sides because the gradient pulls the near side toward the moon and lets the far side lag behind, and the middle gets squeezed. The effect is strong enough that the ocean rises by a meter or more twice a day, and even the solid rock of the Earth flexes by a small amount under the same gradient. You do not feel the rock moving, but it does move, centimeters at a time, every 12 hours. The galactic tide works the same way. Only the thing being stretched is the sun's entire domain. The Milky Way's mass is not sitting at one point. It is spread across a disk, with the sun embedded inside it. The pull from all that mass acts a little differently on one side of the sun's territory than on the other, and that difference, applied across tens of thousands of astronomical units, is the galactic tide. It does not care about the sun's plans. It does not know the sun has planets. It simply stretches whatever sits inside the gradient, and what sits inside the gradient, past the planets, is ice. Now follow what that stretching does to a single object. Picture a chunk of ice orbiting the sun at 50,000 astronomical units. Its orbit is enormous. One trip around takes roughly 10 million years. It is far enough out that the sun's grip is thin, and the galactic tide, even though it is gentle by any ordinary standard, has 10 million years per orbit to work on it. At certain points in the orbit, the tide pushes the object slightly, not toward the sun, not away from it, but sideways, in a way that tilts the shape of the orbit. Over many passes, orbit after orbit, millions upon millions of years, that tilting accumulates. There is no single moment when the orbit breaks. Each pass adds a tiny change, smaller than any measurement could catch on a single revolution, but compounding over thousands of passes until the cumulative shift is enormous. The closest point of the orbit, the place where the object dips nearest the sun, slowly drops. An orbit that once stayed entirely in the deep cold begins, over time, to reach farther inward. 50,000 astronomical units at the far end, but now dipping to 1,000 at the near end, then 500, then less, and then one day, after millions of years of silent reshaping, the near end of the orbit dips close enough to the sun for ice to warm and gas to boil off, and a tail forms, and we call it a comet. The bright streak in the sky is not a sudden event. It is the final act of a process that began before any civilization existed, before any species that would eventually watch the sky had appeared. The tide did not grab the object and throw it inward. It nudged the orbit, gently, a little more each pass, until the orbit delivered the object into the warmth on its own. And the tide does not work alone. Between the slow, steady reshaping and the appearance of a comet in the inner system, there is a second force. Stars pass near the sun. Not often, and rarely close by everyday standards. But over billions of years, dozens of stars have drifted within range of the outer cloud, and each passage gives a gravitational kick to whatever happens to be nearby. These kicks are sudden, direct, and random compared to the tide's slow patience. A single passing star can shove a cluster of icy bodies onto new orbits in a few tens of thousands of years, what the tide alone would need hundreds of millions of years to accomplish. The two forces work in concert. The tide maintains a slow, baseline trickle of comets falling inward. The stars produce bursts, brief surges of new arrivals separated by long stretches of quiet. Together they keep the inner system supplied with messengers from the edge. You might ask why the cloud has not been emptied by now. 4.5 billion years of tidal reshaping and stellar kicks, and the comets are still coming. The answer is that the tide is selective. It does not act on every orbit equally. The torque it applies depends on the orientation of the orbit relative to the galactic plane, and at any given time, only a small fraction of the orbits out there are lined up in a way that lets the tide push them inward. The rest drift on paths the tide cannot reach until the slow precession of their orbits eventually rotates them into a vulnerable angle, which itself takes hundreds of millions of years. The cloud feeds the inner system the way a reservoir releases water through a narrow channel. The supply is vast, but the opening is small, and the flow is slow enough that the reservoir lasts for the full age of the solar system and beyond. That is what makes it so difficult to see from the inside. The trickle is real, but it is so thin that we might wait centuries between arrivals of a truly long-period comet, and each one looks like a singular event rather than the latest drop from an ancient, patient source. There is something about the timing here that I did not fully take in until I followed the mechanism all the way through. The comet you might see some clear night, a pale smear low on the horizon, arrived in the inner system after a journey of orbital reshaping that lasted longer than the entire history of complex life on Earth. Every nudge, every fractional tilt of the orbit happened in a silence no instrument was there to record. By the time the ice finally reaches the sun and a tail lights up, the process is already finished. What we see is not the event. It is the receipt. The long, invisible work was over before we even knew to look. So, the galactic tide breathes through the solar system, slow and patient and selective, peeling off a few objects at a time over timescales the mind has trouble holding, and passing stars add their own occasional push. Both forces are real. Both are working right now, and neither one requires anything unusual to explain. They are just gravity, applied over distance and time. But all of this has been described from the outside, from the scale of the cloud and the galaxy. We have not yet asked whether there is anything closer to home, anything a single body standing on a planet might already know that works the same way. Is there a tide you have already felt without knowing it had a name? Yes, you have. Not something like it, not a distant relative of it. The same force, the same physics, acting at a scale you can stand on a beach and watch. When the tide comes in and the water climbs the sand, you are looking at differential gravity, the moon pulling harder on the near water than the far water, the exact mechanism we just spent so long tracing across light years of empty space. We reached for the ocean earlier, when we needed something to explain the galactic tide and treated it as a convenient comparison. It was never a comparison. It was the same thing, met up close, before we knew its name. The galactic tide and the ocean tide are not two things that resemble each other. They are one thing, wearing different sizes. There is, when you get down to it, only one tidal force in all of physics. One equation. It says that whenever gravity pulls on an extended object, it pulls a little harder on the near part than the far part, and that difference stretches the object along the line toward the source and squeezes it from the sides. That is the whole of it. Feed that equation the moon and an ocean, and you get tides that lift ships twice a day. Feed it the galaxy and the Oort Cloud, and you get comets pried loose over millions of years. Feed it a black hole and a human body, and you get something no one survives. The numbers change. The machine does not, and it is running on you right now. As you lie here, the moon is somewhere above you or below you, and it is raising a tide in the water of your body, the same pull it raises in the sea. You will never feel it, and the reason you will never feel it is worth understanding, because it is the same reason the ocean does feel it. The size of a tide depends on how large the thing being stretched is. An ocean is wide enough that the difference in the moon's pull across it adds up to something your eyes can see. A human body is so small that the difference in pull from one side of you to the other is almost nothing. A stretch so faint that no instrument tucked inside you could register it. But it is not zero. The moon is tugging on you, unevenly, every second of your life. The Earth does it too, and more strongly. One end of your body is closer to the center of the Earth than the other, which means the Earth's gravity is very slightly stronger at one end of you than the other. That difference is a tide, the Earth stretching you along its own pull, faintly, without pause. It is still far too small to feel. But it is larger than the moon's tide on you, because the Earth is so much closer. The same reasoning that tells you the galactic tide is gentle at the edge of the cloud tells you the Earth's tide is gentle on your body. Closeness and mass and size, those three things set the strength of every tide there has ever been. Change any one of them, and the tide changes with it. That is why the moon, small but near, raises a larger ocean tide than the sun, which is vastly more massive but vastly farther away. If you cannot feel any of this, you might fairly ask why it counts as the same force as the one moving the ocean or the one inhaling comets. The answer is that the same force does not mean the same strength. It means the same rule. A whisper and a shout are the same thing, sound, differing only in how much energy is behind them. The tide on your body and the tide on the Oort Cloud differ only in how much mass is pulling, from how far, across how large a thing. There is no point along that range where the force quietly changes its nature and becomes something else. It is one continuous thing, from the unfeelable stretch in your own tissue all the way out to the slow unmaking of orbits a light year away. It is the same continuum that, at its far extreme, would draw a falling astronaut near a black hole into a thin stream of matter, one end of the body pulled away from the other by a stretch that grows unbearable as the distance shrinks. That is only the body tide you carry now, turned up until it kills. The line between harmless and fatal lies entirely in the numbers. Picture it as a single machine with 3 dials. One dial for the mass doing the pulling, one for the distance, one for the size of the thing being stretched. Turn the mass dial up to a galaxy, The size dial up to a cloud tens of thousands of astronomical units across, and you get the slow breathing we traced last time. Comets peeled off one by one over the age of the solar system. Turn the mass dial down to a moon. The distance dial in close, and you get water climbing a beach. Leave the size dial set to the width of a person, and you get a stretch too small to notice. Nothing about the machine changes between those settings. You are turning dials on the same device that runs the edge of the solar system. There is something quietly remarkable in that, and I will say it plainly rather than dress it up. The force doing the most distant work in the sun's whole territory, the slow, patient pull that decides which comets fall inward, from a region so far away that light needs more than a year to cross it, is the same force you can watch with your own eyes on any coastline, lifting the water a few inches up the sand. You do not need a telescope to see the mechanism that shapes the edge of everything the sun owns. You need a shoreline and the patience to wait 6 hours. The tide that has no water, out there in the dark, and the tide that does, here at your feet, are the same sentence written at 2 different sizes. The force, then, is familiar, even if the place it works is not. And that turns the next question. We have been following the tide as if the only thing that mattered were the orbit, the path, the slow geometry of a body drawn inward. We watched the orbit change and called the result a comet, as if the comet were the orbit. It is not. The orbit is only the delivery. A comet is a physical object, a mountain of ice that has sat in the deep cold, untouched, for the entire age of the solar system. And now, after millions of years of that gentle pull, it is finally crossing the line from the dark into the warmth. What does that crossing do to the thing itself? What happens to a mountain of ancient ice the first time? In 4.5 billion years, it begins to feel the sun. It breathes. Not the way you or I do, but in the only way an object made of frozen gas can. As it drifts inward and the faintest trace of warmth reaches it, some of that frozen material turns straight from solid to gas and streams off into space, wrapping the body in a thin haze and trailing behind it. That escaping gas is the breath, and the surprising part, the part that took even the people studying it a moment to absorb, is how far out the breathing can start. It does not need the sun to be close. It barely needs the sun at all. What it needs is the smallest change, the difference between the deep cold of the outer cloud and the slightly less deep cold of the region just past the giant planets. That difference, almost nothing by human standards, is enough. We are not guessing about this because there is one we have been watching do it. In 2021, 2 astronomers, Pedro Bernardinelli and Gary Bernstein, went back through years of old survey images, photographs of the sky taken for an entirely different purpose and then archived. Buried in that data was a faint moving dot that no one had flagged at the time. They traced it across the frames, worked out its path, and realized they were looking at something enormous falling in from the deep outer cloud on an orbit so long it had likely not been near the sun in millions of years. The object was given their names. It is one of the largest comets ever found. It had been sitting in those archived images for years, a giant in plain sight that no one had any reason to single out. Even an object the size of a small country, falling in from the dark, can pass through our own records unremarked until someone goes back and asks a different question of the same pictures. The size is the first thing that stops you. A typical comet, the kind that swings through every few years or decades, has a solid core a few miles across, a dirty iceberg you could walk around the base of in an afternoon. This one is roughly 120 kilometers across, something like 80 miles, 10 times the width of an ordinary comet. And because volume grows with the cube of width, 10 times wider means about 1,000 times more material. If an ordinary comet is a boulder, this is a small country's worth of ice, a frozen mountain range moving through the dark as a single piece. A body that big has enough of its own gravity to have pulled itself into a rounded shape, more like a small world than a loose pile of rubble. Nothing that size was supposed to be out there falling inward. Most things that large stay put. one detail about it does not fit at first. When astronomers turned their instruments on it, the object was already active, already venting gas, while it was still farther from the Sun than Saturn, more than 1 billion miles out. At that distance, the Sun is a brilliant point, not a source of real heat. The temperature out there sits not far above the coldest anything in nature gets, down near what physicists call absolute zero, the point where atoms themselves nearly stop moving. And yet the thing was breathing. Something was boiling off a body that, by any reasonable expectation, should have been frozen solid and silent. The gas they detected was carbon monoxide, and that single fact explains the whole puzzle. The answer is a matter of which ice. Not all frozen things wake at the same temperature. Water ice, the stuff most comets are mostly made of, needs the Sun fairly close, somewhere inside the orbit of Jupiter, before it warms enough to turn to gas. But carbon monoxide ice is far more delicate. It turns to gas at a temperature only a little above absolute zero. So, while the body is still deep in the cold, far too cold to release any water, the trace of warmth from a distant sun is already more than enough to wake the carbon monoxide. Think of dry ice sitting on a table in an ordinary room. The room is not hot. By any standard that matters to you, the room is cool. But to dry ice, that mild room is a furnace, and it fumes away into white vapor without anyone having to heat it at all. The carbon monoxide in this comet is doing the same thing. The sun's distant glow, useless for melting water, is a furnace for the most fragile ice the comet carries. There is something else worth knowing about this particular giant, and it changes how you read the breathing. It is never going to come close to us. At its nearest approach to the sun, still a few years away, it will not even cross inside the orbit of Saturn. It will turn around out there in the cold and begin the long fall back toward the deep cloud it came from, which means its surface has never been baked. Most comets we see have been cooked by repeated close passes, their original outer layers blown off long ago. This one is close to untouched, carrying ice that has sat undisturbed since the solar system was forming. We are not watching an old comet repeat a familiar trip. We are watching a pristine relic exhale. Possibly the first time anyone has caught a body this large doing it, this far from the sun, with its first surface still on. I keep catching myself using the word breathe, and I am not sure I should stop. There is no biology here. Nothing is alive on that frozen mountain. What is happening is pure physics, gas escaping a solid as the temperature ticks up by a few degrees. And still, every time I describe it, the words that arrive are the words for a living thing waking, stirring, exhaling after a long sleep. Maybe that is a failure of language, our habit of reaching for the body to describe everything else. Or maybe it is the most accurate thing we have, because what we are watching, after 4.5 billion years of stillness, is an object responding to its surroundings for the first time in a span longer than there has been life on Earth. The line between a thing waking and a thing merely warming is thinner than it sounds. That is what crossing the line does. A body that sat frozen and inert for the entire age of the solar system feels the faintest distant warmth and begins, gently, to come undone, shedding its most fragile ice into a tail. But the size keeps the question open. An ordinary comet is a fragment, a chip off something larger. This is 1,000 times the mass, a mountain range of ice that has been waiting in the dark since before the planets finished forming. It did not drift gently to where it is. Something put it there. Small things scatter easily. Something this large does not end up at the edge of everything by accident. So, where was a mountain like that born? And was it ever really ours to begin with? It was born here. Not at the edge where we found it, but in the warm, crowded heart of the young solar system, somewhere out among the giant planets, 4.5 billion years ago. Every object in the cloud, every frozen mountain in that distant shell, almost certainly began its life close in the same region and at the same time as Jupiter and Saturn and the worlds we know. The cloud is not where these things were made. It is where they were sent. They could not have been made where they sit now. To build a body, you need raw material packed close enough together that pieces collide gently and stick, then collide again, growing grain by grain into something larger. That requires a crowd. Near the forming planets, the young solar system was dense and busy, full of icy debris bumping and merging. Out at tens of thousands of astronomical units, there is almost nothing, and what little there is moves so slowly and sits so far apart that two pieces might drift for the age of the universe without ever meeting. You cannot assemble a 120-kilometer mountain in a place that empty. Whatever is out there was built somewhere fuller and then moved. Moving it took the planets, and it was not gentle. A giant planet like Jupiter is more than 300 times the mass of the Earth, and when a small icy body wanders too close, the planet's gravity grabs it, swings it around, and flings it away on a completely different path. The planet barely notices. It is so much heavier than the icy body that the encounter leaves its own orbit essentially unchanged. But for the small body, everything changes. It arrives on one orbit and leaves on another, sometimes thrown inward, often hurled outward into the dark at tremendous speed. This is not a rare accident. In a young, crowded system, near misses with a giant planet happen constantly, and over millions of years a single giant can fling a staggering number of bodies onto new paths, a few at a time, encounter after encounter. Watch a hard break on a pool table to feel the shape of it. The cue ball comes in fast and strikes the packed cluster, and the light balls go rocketing to the rails while the cue ball, having given up most of its motion, rolls only a little way on. Momentum is traded. The thing that was moving fast slows, and the things it strikes fly off to the edges. Now make the cue ball thousands of times heavier than everything it hits. It barely slows at all, and the small balls scatter even harder. That is the giant planet and the icy body. The planet is the heavy ball that keeps its line, and the comet is the light one flung to the rail, out toward the edge of the table, except the table is the solar system, and the rail is tens of thousands of astronomical units away. But a single kick does not build a cloud, and there is a real problem hiding in that. An object flung outward by Jupiter does not simply settle at the edge. Its orbit still loops all the way back to where it started, back into the planetary region, where Jupiter is waiting to kick it again. Most objects that meet Jupiter this way get kicked harder each time until they are thrown clean out of the solar system entirely, lost to interstellar space. Jupiter is less a builder of the cloud than a bouncer at the door, ejecting far more than it ever keeps. So if the strongest planet mostly throws things away, how does anything stay? The rescue comes from a force we already followed. The more distant giants, Saturn and Uranus and Neptune, give gentler kicks, lofting bodies to enormous distances without quite ejecting them. And once a body is way out there, creeping along the far slow end of a vast orbit, the galactic tide and the occasional passing star go to work on it, the same slow pull that inhales comets, running in the other direction. They lift the near end of its orbit, the point of closest approach, away from the planetary region, raised high enough that near point no longer dips back among the giants and the object stops coming home to be kicked. It is decoupled, parked, saved. It is a two-step trick. The planets supply the distance. The galaxy supplies the safety. Neither one alone could have made the cloud, and the fact that both happen to act on the same objects is part of why the cloud exists at all, which means the cloud is a record of its own making. Every orbit out there is a frozen snapshot of the chaos that flung it, and the chaos was considerable. In its first few 100 million years, the solar system did not look like the tidy diagram. The giant planets were shifting their orbits, drifting through new arrangements, and that migration scattered icy bodies by the trillions. Most were lost. A small fraction were caught at the right moment and stored. The cloud we have been tracing is the survivors of that early violence. the material that happened to be lofted and lifted at just the right time, holding the shape of a catastrophe that ended before the first living cell appeared on Earth. The cloud, seen this way, stops being a far-off curiosity and becomes something closer to a consequence. The most distant thing the sun owns, the cold shell at the very edge of its reach, is made of refugees from the center. That frozen mountain breathing in the dark was once a piece of the busy inner system, a neighbor to the forming planets, and it was thrown out and never allowed back. The edge of home is built from what the heart of home expelled. What gets me is that gravity does none of this on purpose. There is no cruelty in it, no intention, no decision to cast anything away, and the result still looks exactly like exile. The things farthest from the sun are the things the sun's own planets cast off, drifting at the border ever since, too far out to return and too bound to the sun to leave. That gives us the origin at last. Born in the warm crowd, flung outward by the giants, lifted clear by the tide, and stored at the edge as a fossil of the solar system's violent youth. It is a clean story, and it has one quiet assumption buried inside it. If the planets built the cloud by throwing out the solar system's own material, then everything in the cloud should be ours, homegrown. Every last frozen mountain a child of this sun. But when you look closely at where all that material might really have come from, that assumption starts to come apart. How much of the cloud was never ours at all? The sun was not alone when it was born. New star is. Stars form in clusters, the way a city block fills in all at once rather than one building at a time, dozens or hundreds of new suns condensing out of the same enormous cloud of gas and dust, lighting up within a few million years of each other. The sun was probably part of a cluster of several hundred stars, packed into a region far smaller than the sun's current neighborhood. The nearest star to us now sits a little over 4 light-years away, or about 270,000 astronomical units. In the birth cluster, some of those same stars were at distances measured in the hundreds to low thousands of astronomical units, closer to us than some of the material in our own forming cloud, inside the very zone where the Oort Cloud was taking shape. Every one of those stars was doing the same thing the sun was doing. Growing planets, scattering icy debris outward, building its own cloud of material in the region between its planets and open space. And because the stars were so close, those forming clouds were not sealed containers. The outer edges of each cloud extended into the same space as the outer edges of its neighbors. They were not touching in the way solid things touch. They were overlapping in the way fields of influence overlap, each cloud's gravitational reach blending into the next. While that crowding lasted, material scattered from one star could drift gently into another's gravitational domain and be weakly captured. An icy body flung to high aphelion by Jupiter's kick might sail out past where the sun's grip barely holds, into the intermediate space where a neighboring star is pulling just as hard, and settle into an orbit around that neighbor instead. Or the reverse. A body from a neighbor's disk, flung outward by that star's own giants, might drift into our region and end up circling the sun. The exchange was not organized. It was the byproduct of proximity, gravity, and time. Two stars building their clouds too close together, inevitably sharing material they never reached out to take. The boundary between one star's material and another's was not a line anyone drew. It was just wherever the gravity happened to balance. Think of a school playground at full capacity. Every child carrying a handful of small objects, running and bumping into each other for hours. By the end of the afternoon, when the bell rings and everyone goes home, what is in each child's pocket is not entirely what they arrived with. Some of what they carry was pressed into their hand in a collision. Some was picked up off the ground where it fell from someone else. The exchange was never deliberate. It happened because the space was crowded and the contact was continuous. The birth cluster worked the same way, except the children were stars, the objects were icy planetesimals, and the afternoon lasted tens of millions of years. When the bell finally rang and the cluster began to come apart, each star left carrying a mixture. This is a hypothesis, not a settled picture. The Sun's birth cluster is inferred rather than observed. It dispersed long before anything was alive to study it. The exchange of material is modeled in simulations rather than measured directly, and the precise fraction of the Oort cloud that arrived from neighboring stars depends heavily on how dense the cluster was and how long it stayed packed together, which we cannot know with precision. These are real uncertainties, and the simulations give a range rather than a fixed number. But the range is striking. When researchers run models with reasonable estimates for the cluster's size and lifetime, the captured fraction consistently comes out large. In many scenarios, the majority of the outer Oort cloud could be material that originated around other stars, with some models pushing that fraction well past half. The inner cloud, sitting closer in where the planet's influence is still strong, likely contains mostly homegrown material. But the outer shell, the most distant and most tenuously held part, is where the captured fraction may dominate. The outer cloud, the part that extends from tens of thousands of astronomical units out toward the tidal limit, may be less a product of this solar system than a collective archive, assembled from the disks of dozens of stars that no longer exist anywhere near our neighborhood. When the cluster finally dispersed, each star drifted off into its own corner of the galaxy, and the birth neighborhood ceased to exist as a neighborhood. The stars that once passed within thousands of astronomical units of each other are now light years apart in every direction, each carrying its cloud, each cloud a composite. The dispersal did not separate the material by origin. It just moved the owners apart. Every star that came from that cluster is probably orbiting right now, with a cloud that carries a fraction of its siblings' histories, mixed in among its own, indistinguishable by orbit alone. The exchange was mutual and unconscious, driven entirely by proximity. Every star near us was giving material away at the same time it was receiving it. If the Sun captured ice from its neighbors, those neighbors were capturing ice from the Sun. We did not take anything that was not also being taken from us in equal measure. What you are left with, when you let the word theft go, is something closer to heritage. A cloud built not from one source but from many, carrying frozen material that formed around suns that have long since moved beyond the reach of any instrument we have ever built. That ice has been circling here, indistinguishable from the rest, for the entire age of the solar system. The cloud, if the simulations are anywhere close to right, is not ours in the way we assumed when we called it the Sun's territory. It is a mixture assembled in a nursery that no longer exists, from material that no single star can claim. The cloud cannot tell us which is which, at least not by appearances. Two chunks of ice in the same orbit look identical, but they may have formed around different stars, in different disks, from dust with slightly different chemical histories. If there is a difference to be found, it would have to be in the ice itself, a signature so faint we have barely begun to look for it. Is there a way to tell an alien comet from one that was always ours? And if there is, what would the answer actually tell us about what it means to call the cloud home? The simpler of the two questions was whether we could tell the difference at all. Whether a comet from a sibling star's disk looks any different from one born in our own. That question has a scientific answer, and it lives in the chemistry of the ice. But before we follow that path, the harder question deserves examination on its own. Not, is there a way to distinguish them, but what would the distinction actually settle? Because the answer to the second question turns out to change the shape of the first, not the answer to it. The shape of it, what we are willing to count as evidence, depends on what we are trying to settle, and we have not quite decided that yet. Belonging, at the level of matter rather than ownership, means something specific. An icy body orbiting the Sun right now is under the Sun's gravitational authority. It is held here. It responds to the Sun's gravity, to the galactic tide, to the perturbations of Jupiter. Its orbit was shaped by the history of this solar system. In every physical sense that admits of measurement, it is part of this system. The question of where its atoms were assembled, 10 or 20,000 astronomical units from here, in a protoplanetary disk around a star that has since traveled 300 light-years in a different direction, does not enter the physics. The orbit does not carry a note about parentage, but we keep wanting it to. We want ours to mean something more than gravitationally bound here now. We want it to mean made here, of our stuff, continuous with our history. And that wanting runs into something the physical universe is not designed to provide. The ice that formed around another star 4.5 billion years ago has been orbiting here, following this sun, shaped by this system's tides and encounters and migrations for longer than complex life has existed on Earth. Every comet shower it was nudged toward, every long, slow orbit under the galactic tide, every near encounter with a passing star, it was there, part of it, as fully as anything born here. The word native assumes an identity fixed at the moment of formation. But 4.5 billion years of shared gravitational history is not nothing. A body that has been shaped by the same tides, the same stellar encounters, the same slow sculpting we have been tracing, has a history in this system that is real, regardless of where the first grain of its ice nucleated. The captured material does not announce its origin. A chunk of ice from a sibling star's disk and a chunk from our own disk, sitting side by side in the outer cloud, are following the same physics, responding to the same forces, shaped by the same history since the moment of capture. They do not behave differently. They do not age differently. Their orbits carry no marker distinguishing one from the other. You could examine the trajectory of either one for 1 million years and learn nothing about which star made it. That information is not in the motion. The thing that stopped me in this was not the fraction, whether it was half the cloud or 90%. It was the simpler fact underneath. There is no moment at which captured material becomes native. It is captured, and then it orbits, and it keeps orbiting, and nothing happens to it that changes its status from one category to the other. No clock runs out. No threshold is crossed. 4.5 billion years of shared history do not count as naturalization, because there is no process for naturalization. The concept has no mechanism in the physics. And the reason the physics has no mechanism is that origin is not a property gravity tracks. What gravity tracks is position and momentum. You are here. You are moving at this speed. You are held by this mass. Everything else, where you came from, which disk you condensed in, which star's light first struck your surface, is information the orbit simply does not carry. We were asking matter to hold a distinction that matter was never built to record. What we are left with is a different kind of ours. Not ours by origin, not ours by manufacture. Ours by present orbit, by gravitational membership, by participation in a shared history that has been running for 4 billion years and is still running now. The stranger part of this is that it is what ours has always meant. Even for the material we never doubted. The iron in the Earth's core fell from ancient supernovae that exploded before the sun existed. The water in the oceans arrived on comets and asteroids from elsewhere. The calcium in bone, the iron in blood, none of it was made here. We built this world, and ourselves, from material that was already ancient when the solar system formed. If the Oort Cloud's extrasolar fraction unsettles the concept of ours, the same argument runs all the way back to the first grain of dust that gathered to make the planets. The precision of it runs all the way down. The boundary of home has never been a boundary of origin. It has always been a boundary of current gravitational membership, of shared history, of what is participating in the same ongoing story. The material in the outer cloud, whatever star it formed around, has been part of this story since before there was anything alive on this planet to call anything home at all. The word itself, home, turns out to be about the present, not the past, about where something is and what it is part of now. Not where the atoms that compose it happened to condense 4.5 billion years ago. All of that is the harder question, and it does not have an uncomfortable answer so much as a clarifying one. But the simpler question is still sitting there, and it has its own kind of weight. Whether we can draw a line between what formed here and what was captured, Not to settle the ownership problem, which we have just seen cannot be settled that way, but to read the history of the cloud itself. Different stars produce subtly different ratios in their elements, slight variations in their isotopes, signatures left in the material they made. If those signatures survive in the ice, then the cloud is not just an archive of this solar system's violence and migration. It is a library of other stars, their chemistry preserved in frozen form, waiting in orbits no one has yet thought to read for their original handwriting. Is the faint writing still there? The writing is there. In principle, every piece of ice in the outer cloud carries a record of its formation, encoded in the precise ratios of its atoms. Carbon that formed in one stellar environment will have a slightly different balance of heavy to light variance than carbon that formed in another. The same is true of hydrogen, of nitrogen, of oxygen. These ratios do not change easily. They were set when the atoms nucleated in the interior or atmosphere of a dying star, and they survived the journey from that star to the nebula that made the solar system, and then the 4.5 billion years since. The record is old and the record is real. The question is whether we can read it. What actually carries the record is a property of atoms called isotopes. Atoms of any given element come in different versions, all chemically identical but differing in weight. Carbon has a lighter form and a heavier one. Hydrogen has a heavier twin called deuterium. Nitrogen, oxygen, and sulfur all have their variants. The ratio of heavier to lighter reflects the nuclear processes that made them, and those processes run differently in different stars, at different temperatures, under different pressures. Two rivers draining different mountain ranges carry different dissolved minerals to the sea. You can read the rock each river passed through in the chemistry of the water. Isotopes work the same way. The material condensed around a star, and as it did, it recorded the nuclear history of that environment in the balance of its heavy and light atoms. In ocean water, deuterium makes up about 1 in every 6,400 hydrogen atoms. In some comets, the ratio is roughly twice that. In other stellar environments, it varies further still. These differences are small, but they are carried with a precision that survives billions of years, and that precision is what makes them useful. We know the method works because we have found its proof. Embedded in some of the meteorites that have fallen to Earth are grains so small you could fit hundreds of them on the period at the end of a sentence, and yet they are not from the solar system. Their isotopic ratios are wildly different from anything that formed here, so different that no process within our own planetary neighborhood could have produced them. These are pre-solar grains, material that condensed around other stars before the sun existed, survived the journey through interstellar space, survived the formation of the solar system, survived being locked inside a rock for 4.5 billion years, and arrived intact enough to measure. Their isotopic ratios are unmistakable. We are not inferring a foreign birthplace. We are reading it directly, in ratios that point somewhere else entirely. The method, in other words, works. The principle is completely sound. The problem is that the method works on samples we can hold, analyze in a laboratory, and return to as many times as necessary with the best instruments we have. A comet in the outer Oort cloud is another situation. It is tens of thousands of astronomical units away, a frozen body smaller than a major city, dark as coal and venting nothing into space. We cannot send a probe. We cannot collect a sample. We cannot point a spectrometer at it and gather a useful signal. We can barely confirm that it exists. The writing we want to read is on a page we cannot yet reach. The objects we can study are the ones that come close. When a long-period comet dips into the inner solar system and the sun warms it enough to produce a coma, there is a brief window. The outgassing creates an envelope of gas around the nucleus, and that envelope can be analyzed. We have measured deuterium to hydrogen ratios in a handful of comets that way, along with carbon and nitrogen isotope ratios. None of it is easy. The coma is diffuse. The signals are faint. The comet is moving. The window is short, but we have managed enough measurements to establish that the ratios vary, that different comets carry different proportions, that the outer solar system is not isotopically uniform. Some of the comets we have measured match what is expected for material that formed close to the Sun in the warm inner disk. Others do not match as cleanly. The spread is real. Whether any of the outliers trace their origin to another star's disk is a question we do not yet have the resolution to answer clearly. Two things keep blurring the line. The first is processing. A body that has spent 4.5 billion years in the outer cloud has been slowly altered by cosmic ray bombardment, by the faint chemistry of ultraviolet radiation on its outermost grains, by the occasional mild warming of a close stellar encounter. These processes shift isotopic ratios over long timescales. The original stellar signature, the one set at the moment of formation, gets partially overwritten. By the time we measure it, we are reading something between the original record and a palimpsest, a manuscript scraped and written over, but with the older text still pressing faintly through the newer, blurring what we came to find. The second is mixing. Comets are assemblages built from grains that formed at different temperatures and different distances. Some carry one isotopic history, some carry another, and when the comet forms, they blend. The resulting ratio is a composite, averaged across the mixture, and the clean fingerprint of a single stellar birthplace, if it ever existed purely, has been folded in with everything else. Both of those difficulties are failures of measurement, not of principle. We know the writing is there. We have seen enough of it, in the pre-solar grains, to trust the method completely. And still, when it comes to the thing we actually want to read, the body in the deep cloud, we are working at the very edge of what any instrument can resolve, and mostly well beyond that edge. We know the answer might be there. We just do not yet have the tools to reach it with any confidence. There is a particular kind of patience required for that situation. Not the patience of waiting for an answer, but the patience of holding a question open because closing it early with the tools available now would give the wrong kind of resolution. The scientists working on this are not stuck. They are waiting for the instruments to catch up to the question. None of this means the reading will never happen. Instruments improve. Methods grow more sensitive. Each new comet that passes close is another data point on a picture that is still mostly blank. What we have is a proof of principle from the pre-solar grains, a recognition that variation exists in what we have measured, and an understanding of exactly what is standing between us and clarity. The faint writing is there. Reading it will take time. But there is another way into the question of whether the solar system exchanges material with other stars, one that does not require reaching into the deep cloud at all. Some objects do not fall inward after a slow tidal nudge over millions of years. They arrive from outside the solar system entirely, on trajectories that the Sun did not produce, carrying their chemistry into the inner system where we can actually look at them. What do we learn when one of those visitors comes close enough to study? In 2017, an object appeared in telescopic images moving on a path the solar system could not have produced. Astronomers at a survey telescope on Maui noticed it first, a faint point of reflected light tracing a hyperbolic arc through the inner system. It had come in from outside the solar system, swung past the Sun, and was already heading back out by the time anyone realized what it was. That had never happened before in recorded observation. Every comet, every asteroid, every object tracked until then had been ours, locked into orbits the Sun's gravity could hold. This one was not. What confirmed it was the velocity. At any given distance from the Sun, there is a maximum speed a bound orbit allows. This object was moving well beyond that limit by tens of thousands of miles per hour, enough that the Sun's gravity could bend its path but could never hold it. The direction it had come from pointed between the stars, toward a region of the sky with no known solar system source. It was on a one-way trip through, and it had been traveling that path for longer than there have been humans to look for it. The object was named ʻOumuamua, from a Hawaiian word for a messenger arriving from far away. What it looked like was strange. Its brightness varied so dramatically as it tumbled that it appeared either extremely elongated perhaps 6 times longer than it is wide, or possibly flat, shaped more like a disk than like any familiar rocky body. It produced no coma, no tail, no visible outgassing, and then, as astronomers tracked it leaving the solar system, it accelerated slightly more than the sun's gravity and sunlight pressure together could explain. The acceleration amounted to a small but persistent push, consistent across weeks of observation, which ruled out measurement error. It was reproducible, it was real, and it had no agreed explanation. The most widely discussed possibility involves sunlight pressing on an unusually thin, low-density object. There are others. None has been confirmed. Oumuamua left the solar system with its nature still open. 2 years later, in 2019, a second interstellar object arrived. This one was found not by a professional survey, but by an amateur astronomer in Crimea, Gennady Borisov, scanning the sky with a telescope he had built himself. He noticed a faint smear of light, moving in a way that did not match any known solar system body, and reported it. Analysis confirmed it was arriving from outside the solar system on a hyperbolic trajectory. But Borisov was different from Oumuamua in almost every other respect. It had a coma. It had a tail. It was behaving exactly like a comet. The chemistry that emerged from its coma is what changed the frame. Borisov carried water vapor. It carried carbon monoxide. The ratio of deuterium to hydrogen in its water was roughly twice the ocean value. Within the range of ratios measured in comets from here, Borisov appeared richer in carbon monoxide than most solar system comets we have measured, but comets from here vary considerably in their carbon monoxide content, and Borisov fell within that variation. When researchers analyzed the full mix of volatiles escaping its surface, they found a composition broadly consistent with solar system comets. Not identical, with differences worth studying, but recognizable. A comet that formed around another star, out of material that had never been part of the sun's disk, produced chemistry close enough to our own that the same processes were clearly at work. Volatile-rich ice, the same basic ingredients, the same rough ratios. If Borisov had come from within the solar system, its chemistry would not have stood out. From just 2 detections in the space of a few years, with survey capabilities that were not designed to find interstellar objects and were covering only a small fraction of the sky, researchers estimated that the inner solar system may contain anywhere from hundreds to several thousands of similar interstellar visitors at any given time, passing silently through on hyperbolic arcs that never become orbits. Over the billions of years the Sun has been in its current region of the galaxy, it has probably encountered millions of interstellar objects large enough to be called comets and lost a comparable number to the interstellar medium in the other direction. The solar system is not receiving occasional travelers. It is inside a continuous, slow exchange of material between stellar systems that has probably never stopped. And if the exchange is continuous, it runs both ways. The same dynamics that sent Borisov and Oumuamua inward from wherever they formed will be sending objects from this solar system outward into the interstellar medium, into the paths of other stellar systems, where they may be captured or pass through or drift on into the dark between galaxies. What changed between the birth cluster phase and now is not the fact of the exchange but its pace. In the cluster, it happened rapidly, with stars close and the flow dense. In the open galaxy, it happens slowly, a trickle rather than a stream. But it is the same process, never fully interrupted. The cloud is not a closed container. It is a region where 2 flows meet, material coming in from the galaxy and material leaking out from the sun's domain, mingling in the outer reaches before one set continues inward and the other drifts away. Oumuamua was strange enough that the strangeness itself became the story. The shape, the acceleration, the missing coma, the open questions still unsettled. But the detail I find hardest to put down, even now, is not Oumuamua, it is Borisov. A comet formed around another star, out of material that never belonged to this solar system, came close enough to study, and what we found in it was familiar. the ice chemistry we associate with comets here. The same basic volatile mixture, the same kind of object our own cloud produces, shaped by the same processes in a disk around a different sun. There is something in that recognizability that is harder to account for than strangeness would have been. Strangeness keeps its distance, but familiarity walks up and asks to be named. The cloud is open. Material arrives from outside, and material from here drifts outward into the galaxy. The solar system is not a sealed region of space with a fixed inventory. It is a region that participates in a larger circulation, one that has been running since the first stars formed clouds around them, and those clouds touched each other. Which means the image we have been building of the cloud as a vast frozen archive of the solar system's history needs one final adjustment, an archive that continuously receives new material and loses old material is not just an archive. What is it then? What is the right word for a boundary that is never really closed? Harbor. That is the right word for a boundary that is never really closed. Not wall, not edge, not fence. A harbor is an open place where the traffic is the definition, where what makes it what it is not what it keeps out, but what it lets through. The solar system's cloud region, from the outer edge inward to where the planets begin, is the zone where two populations of objects meet, those falling in from outside and those drifting out from inside. Not a wall between the solar system and the galaxy, the place where they overlap. A harbor is not defined by its walls. It is defined by the pattern of traffic moving through it. Ships come in, ships go out, and the harbor is the harbor precisely because it handles both. A port that only received and never sent would fill up and stop working. A port that only sent and never received would empty and stop existing. What makes it function is the flow in both directions, and what makes it a place rather than just a passage is the basin in the middle, deep enough to hold what passes through it while it is here. The cloud is exactly that structure, a basin with a constant slow traffic passing through in both directions, and the basin itself persisting across the traffic. The traffic runs both ways, and we have been tracking mostly the incoming side. The material captured during the birth cluster phase, the continuous slow rain that frequency estimates imply, Borisov arriving with its familiar chemistry, ʻOumuamua, on its unexplained hyperbolic arc. But the outgoing side is just as real and has been running just as long. Every time a passing star nudges something at the outer edge hard enough that the sun's grip cannot hold it, that object crosses into interstellar space and joins the galaxy's pool of free-floating material. Every object sent onto a hyperbolic trajectory by Jupiter's kick, not stored in the cloud but simply expelled, becomes part of the inventory of material that drifts between stellar systems. Some of it finds other stars. Some of it drifts between them forever. Over the full span of the solar system's history, more objects may have been scattered into interstellar space than currently remain in the cloud. The galaxy has received from us as consistently as we have received from it. What keeps it a harbor rather than a sieve is the rate. The loss of material is slow. Most objects in the outer cloud are in stable, long-period orbits, and they remain there for billions of years without being perturbed into escape trajectories. The harbor processes traffic without being emptied by it. The incoming material partly replenishes what is lost. The basin retains its character across the exchange, the way a harbor retains its shape despite the passage of ships, because the ships do not determine the shape of the basin. The sun's gravity does, and the sun's gravity is not going anywhere. The uncomfortable implication of the open harbor is what it says about the container. The container model, the mental picture of the solar system as a closed region with a fixed, identifiable inventory, was always a simplification. Not a useless one, and not entirely wrong, but a simplification layered over something more open. The real solar system has never had a fixed inventory. Since the first materials settled into orbit, things have been leaking out and arriving in. The cloud we have been describing, the one whose structure we mapped and whose formation we traced, is not the same cloud that existed 4 billion years ago. It is the same cloud in the way that a river is the same river, defined by its basin and its course, not by its water molecules. The river's identity lies in the banks, not in the water. The cloud's identity lies in the gravitational basin of the Sun and the orbital structure of its members, not in the specific origin of each piece of ice. A boundary separates, and a harbor connects. That openness has been running for the full age of the solar system. If we could replay those 4 billion years fast enough to watch, we would see the outer cloud as a slowly churning zone, losing objects to stellar encounters and the galactic tide, gaining objects from interstellar space, with the net balance always favoring retention, but the boundaries always permeable. The harbor was not made open by some disturbance. It was never sealed. There was no closed phase that the exchange disrupted. The galactic tide we traced earlier requires the boundary to be permeable, because the tide is the mechanism that couples the inner system to the outer cloud and the outer cloud to the galaxy. The open harbor was implied in the physics from the start. It was always the picture. We just kept drawing the container. The model and the instinct part ways at exactly one point, and that point is worth naming. The solar system as a container is the image we build first. A bounded space with a fixed inventory, because that is how we experience spaces that belong to us. A room, a yard, a country. But none of those are actually closed either. Air moves through a room. Rain falls into a yard. A country's population of atoms is not the same it was 1,000 years ago. The container was always an abstraction pasted over something more open. What has existed, what has always existed, was the harbor. The mind wants walls. The physics provides basins. And knowing that does not dissolve the instinct, but it does change what we are looking at when we imagine the edge of the solar system as a fixed line. The line was never there. The basin is real, and the basin is always open. That distinction, archive and port, both at once, changes what the cloud is. Not only the long-preserved record of this solar system's history, but also the slowly changing expression of where this star sits in the current galaxy. The ice in the outer cloud is both old and new, both ours and not entirely ours, both a record of the past and a register of the present exchange. The harbor holds what is here now, while the traffic moves around it. That is the most complete physical picture we have, and it is a good deal more permeable than any classroom map ever suggested. The harbor has been running for 4.5 billion years. The galactic tide has been peeling objects away the whole time. Stellar encounters have been stirring and scattering the outer edges, and yet the comets that actually reach us imply a cloud more populated than those losses alone would predict, which opens a question that has nothing to do with the traffic and everything to do with the objects themselves. Inside that harbor, 100,000 astronomical units of ice has been orbiting, bumping, slowly drifting for longer than there has been life on Earth. With that much material in motion for that long, something else should have happened. Why hasn't it ground itself to dust? Start with the arithmetic. In the outer cloud, spanning tens of thousands of astronomical units, there are estimated to be hundreds of billions of objects large enough to be called comets. The objects are spaced enormously far apart, but the cloud has been running for 4.5 billion years, and in 4.5 billion years, even very rare events accumulate. Objects drift onto new paths from gravitational nudges. Their orbits precess. Occasionally, two objects whose paths happen to cross come close enough to interact. The question is not whether collisions happen. The question is what they do when they do. If they fragment bodies faster than new material arrives or is preserved, the cloud erodes from the inside as much as from the outside. A rough accounting of the collision rate over billions of years suggests that a significant fraction of the original material should have been ground down to fragments too small to track. The prediction comes from the physics of low-speed collisions between icy objects. At the outer cloud, the relative velocities between objects on nearby orbits are very low, a consequence of how cold and slowly moving everything is at such distances. Low-speed collisions between icy bodies do not always shatter. Sometimes they stick, merging two smaller things into a larger one. But they can also fracture, splitting a body into fragments that disperse. Over many billions of years, with enough collisions, a size distribution that once concentrated mass in larger objects gradually shifts. Larger bodies break into smaller ones. Smaller ones break into smaller still. At some point, the fragments become too small to outgas meaningfully when they drift inward, too small to register as comets, dispersing instead as dust that is eventually swept away by the solar wind. The original population thins. The observation that refuses to fit this picture neatly is the cometary flux. Every year, a handful of new long-period comets are discovered falling into the inner solar system on their first passes or returning from orbits that take millions of years to complete. Working backward from that arrival rate and from the orbital dynamics of how the galactic tide and stellar encounters feed the inner system from the cloud, the implied cloud population runs into the hundreds of billions of objects. That is the reservoir the models require to explain the comets we see arriving. If collisional grinding over 4.5 billion years had depleted the cloud as efficiently as the physics might suggest, starting from any reasonable initial mass, the current population would be a small fraction of what the observations require. The cloud appears too full. Two paths of resolution have been proposed, and both are probably partially right. The first is that the cloud started with far more material than it currently holds. Perhaps 10 times the current mass, perhaps 100 times. If the original cloud held 100 times its current mass, more than 99% of it has been lost over the solar system's lifetime, and what we observe would be the surviving residue of something enormously larger. The second path is that collisions in the outer cloud are less destructive than they appear. At the actual velocities and densities, and with the actual size distribution of icy bodies, many encounters may have resulted in gentle sticking rather than catastrophic fragmentation, and the grinding may have been slower and less thorough than the worst-case calculation. The true answer is probably some combination. A larger original cloud, less thoroughly processed than feared, leaving a residue we are still working to characterize. The plain answer is that we do not know the original mass. Not within a factor of 2, not within a factor of 10. The cloud's initial size is one of the fundamental unknowns of the solar system, sitting alongside the original inventory of water on Earth and the early migration history of the giant planets as questions the evidence cannot yet fully answer. We can constrain the answer from both ends, ruling out values so extreme that nothing could reconcile them with observations, but the range between those constraints is still wide enough that the problem feels open rather than merely unsolved. The comet population itself carries clues worth noting. Among the long-period comets that actually reach the inner system, a small fraction arrive with very little activity, no bright coma, no significant tail, a surface that reflects light more like rock than fresh ice. These are sometimes called Manx comets, named for a tailless breed of cat. Some of them may have already exhausted their surface volatiles in earlier passes that stripped away their outer layers. Others may have formed as rocky bodies in the inner solar system before being exiled outward by the giant planets, carrying little ice to begin with. Either way, their presence says something real about the range of material in the cloud. The cloud is not a uniform reservoir of pristine ice. It holds objects at different stages of depletion, objects of different origins, objects that have already partly undergone the grinding the theory predicts. The tailless comets are the worn-down members, arriving to confirm that the erosion is real, even as they complicate the calculation of how much has been lost. Working on the original mass problem has a quality I find hard to describe cleanly. You know the answer: the current cloud, the comets we observe, the rough population the flux implies. And you know it is a remainder, but the number it is the remainder of has been erased by time. You are doing subtraction, and the number it started from is gone. You can constrain it, bound it, reason about it from multiple angles, but you cannot recover it the way you can recover the age of a rock or the mass of a dead star. 4.5 billion years of erosion, collision, stellar encounters, and galactic tides have been steadily lowering the starting number since before anything was alive on Earth to write it down. The cloud we have been tracing all this time is, in some sense, only the ending of a story whose beginning we will never be able to read in full. What this leaves us with is a cloud best understood as a residue. Its current form reflects both what it started as and what has been done to it, but those two influences cannot be fully separated. We are reading the present state of something whose past state is gone, which is not a failure of the science. It is the science telling us something true about its own limits and about the limits of what any record can preserve across 4.5 billion years. The cloud endures. What we cannot recover is what it replaced. If we cannot recover the original mass, we can at least follow the forces still working on it now. The galactic tide is one, stellar encounters are another, and there is a third mechanism, less discussed than those, that operates at a scale larger than individual stars, stripping the outermost edges of the cloud in a process that is slow, continuous, and essentially irreversible. Not by a single event, not by a passing star or a tidal surge, by something vast and diffuse that the cloud has been drifting through for its entire existence, that has never stopped, and that has been quietly taking the edge of home apart, layer by layer, without any signal we could measure until we looked at what was missing. What does that kind of loss look like, and how much has it already taken? The mechanism is not a star. A single star, even a large one, passes through the outer cloud quickly and leaves. Its gravitational influence peaks during the closest approach and then fades as the star moves on. What the previous act ended with the vast diffuse force stripping the outer edges over the solar system's full lifetime, quietly and without urgency, is something with a different character, not concentrated at a point, not quick, something spread across a volume of space so large that the sun can spend millions of years passing through its gravitational field without any single dramatic moment of closest approach. Giant molecular clouds. Giant molecular clouds are the star nurseries of the galaxy. They are the places where new stars condense out of collapsing gas, and they are enormous. A typical one holds material amounting to hundreds of thousands of times the mass of the sun, with the most massive approaching 1 million solar masses, spread across a region tens to hundreds of light-years wide. A large molecular cloud carries as much mass as several 100,000 stars, but dispersed across a volume that would take light decades or centuries to cross. Nothing so diffuse could be confused with a star or a black hole, but mass is mass, and enough mass spread across enough space still exerts gravitational influence over everything within range. The Milky Way contains thousands of these clouds, concentrated in the spiral arms that the sun's orbit carries it through roughly every 100 million years. When the sun drifts close to one of these clouds, the effect on the outer Oort cloud is slow and deep. The cloud's gravity does not arrive like a wave. It rises as the sun approaches and falls as the sun recedes, over millions of years of passage, and during that time, it adds a tidal field on top of the galactic tide already present. For the inner cloud and the planetary region, the effect is negligible. The sun's gravity there is dominant, and the extra perturbation is too small to matter. But for objects in the outer cloud, sitting at the margin where the sun's grip is already thin, the additional pull from the GMC is enough to nudge some of them past the threshold. Their orbits become unbound. They drift away from the sun toward interstellar space, slowly, without drama. This is not a dramatic event. At the moment an object crosses the threshold and its orbit becomes technically unbound, nothing visible happens. No flash, no signal. The object simply drifts a little further out than before and keeps drifting, and eventually it is gone. The sun cannot call it back. The stripping is in one direction only. A shoreline that loses material to the sea does not get it back. The sand that washes into the water does not return to rebuild what eroded. Each storm takes something and keeps it, and the shoreline that remains is the one that held through all the storms so far. The outer Oort cloud works the same way. Objects stripped by a GMC passage do not orbit back after the GMC has moved on. The sun's gravity was not strong enough to hold them through the encounter, and once they have drifted beyond the tidal limit, the sun's gravity is not strong enough to recapture them. The loss is permanent, the edge is smaller than it was, and the next passage will find a slightly reduced cloud to strip from. Over the solar system's lifetime, the sun has likely completed roughly 20 orbits of the galaxy and crossed through or near spiral arms multiple times. 20 orbits over 4.5 billion years is roughly one orbit every 230 million years, about the time that has elapsed since the earliest dinosaurs appeared. Estimates suggest perhaps 10 to 20 significant GMC encounters across that span, with the most disruptive ones coming when the sun passed close enough to a massive cloud for the tidal distortion to be strong. Each encounter was different because each cloud was different and each passage was at a different distance. Some may have barely registered, others may have sent large numbers of outer objects drifting away. The cumulative effect is not a single wound but a series of small reductions, each permanent, each adding to the total erosion. The outer cloud we see today is not the original outer cloud. It is the outer cloud after perhaps 20 rounds of stripping, each round removing the most marginally bound objects and leaving the rest. The erosion becomes less unsettling when you see exactly what is being stripped. Not the firmly held core of the cloud. Not the ice at tens of thousands of astronomical units held by the sun at something approaching full strength. What the molecular clouds take are the outermost objects, the ones at the very limit of what the sun can hold, sitting right at the threshold where the galactic pull is nearly equal to the solar one. Those objects were always provisional. They were always the territory the sun claimed most weakly, more weakly than anything else it called its own. The GMCs do not strip the interior. They peel the margin, the part that was already on the border of belonging. What the erosion reveals is not that the cloud is fragile. It is that the outer edge of the cloud was always the sun's most tentative claim. What remains after 20 rounds of peeling is the edge that was held firmly enough to survive each one. It is reduced, and it is, in some sense, the edge that was always genuinely there. What the current cloud is, then, is a cloud that has been refined by its own history. Stripped at the margins, surviving at the core, holding in the middle distances the material that was always bound firmly enough to endure. Its current outer boundary is not the original outer boundary. The original extent has been peeled back in ways we cannot reconstruct because the stripped material left no record in places we can observe. We are looking at the cloud after the erosion has happened, not before it. What we know about the original is only what we can infer by examining what is still being lost and working backward as far as the evidence allows, which is not nearly as far as we would like. All of these forces, the galactic tide, the stellar encounters, the GMC passages, share one quality. They are anonymous. They have no scheduled arrival, no measured trajectory, no predicted moment of closest approach. They are statistical tendencies, distributed over millions and billions of years, occurring somewhere in the outer cloud at all times, but never in a way we can point to and watch happen in a human lifetime. But there is one disruption coming that is none of those things. It has a name. It has a measured trajectory. It has a calculated arrival time, more than 1 million years from now. And when it passes, it will do to the outer cloud what the molecular clouds have been doing gradually, but in a specific event we can already anticipate. A star is coming. What happens when we can put a face on the force? In roughly 1.25 million years, a star currently about 64 light-years from the sun will be deep inside the Oort Cloud, not passing nearby, not brushing the outer edge. Inside it, at a distance somewhere between 10,000 and 15,000 astronomical units from the sun, moving through the outermost region of the sun's territory at the closest any star has been predicted to approach in the solar system's foreseeable future. We know this not from guesswork, but from measurement, from tracking the star's movement across the sky over years and combining that motion with its speed along the line of sight. The calculation exists, and it points at a specific star with a specific trajectory, and the trajectory passes through the cloud. Gliese 710 is an orange dwarf. Smaller, cooler, and dimmer than the Sun, carrying roughly 6/10 of the Sun's mass, it would be an undistinguished object in any catalog if it were not moving toward us. Right now, it sits about 64 light-years away, roughly 15 times the distance to the nearest star. To the naked eye, it is invisible, too faint to see without a telescope. It has been drifting toward the solar system for a long time, and it will continue to close the gap until it reaches its closest point and then begins to recede. The whole encounter, from approach to departure, will take millions of years to unfold from beginning to end. The precision of that prediction is part of what makes this star different from every other disruption we have traced. The galactic tide has no scheduled event. Passing stars nudge the clouds statistically, without any single star being named in advance as the cause. Giant molecular clouds drift through the galaxy on timescales too long and uncertain to assign specific dates to. But Gliese 710's movement across the sky and its speed toward us have both been measured carefully, with each new dataset refining the prediction. The range on the closest distance, 10,000 to 15,000 astronomical units, and the arrival time, between 1.25 and 1.33 million years from now, are the best constrained numbers we have for any future significant encounter between the Sun's territory and another star. This one we can point to in the current sky. What those numbers mean physically is worth holding clearly. 10,000 astronomical units is more than 300 times the distance from the Sun to Neptune. The planets, the entire bright warm core we named and mapped and sent probes to, fit inside a sphere more than 300 times smaller than the distance Gliese 710 will pass at. The encounter will not disturb the planets. It will not shake the inner cloud. What it will enter is the outer Oort Cloud, the thinly populated shell of marginally held objects that the galactic tide has been slowly sculpting, that the molecular clouds have been slowly peeling. And out there, at 10,000 astronomical units, the geometry changes entirely. Gliese 710, at that distance, will be pulling on the outermost objects with a force more than half as strong as the Sun's own pull from the same distance. For the tens of thousands of years around the closest approach, the outer cloud will effectively have two suns. Think of someone walking close alongside a still pond, not touching the water, not stepping in. They pass within a few steps of the surface, and the slight disturbance sends a slow wave moving across the water. The wave reaches the far shore. No part of the person ever touched the water. The disturbance was entirely at a distance, through the medium connecting the person to the surface. Gliese 710 will not touch the Sun. It will not enter the inner system, but as it moves through the outer cloud over tens of thousands of years of closest approach, its gravity will reach into the orbits of the objects it passes near, tugging on each one, changing the shape of the orbit, lowering the closest approach point. The star does not push them. It bends the paths they are already on, and some of those paths will eventually bring ice that has been drifting in the dark for hundreds of millions of years, falling inward into the warmth. What follows the passage, in the millions of years after the closest approach, is a comet shower. Objects whose orbits were reshaped by the encounter begin arriving in the inner system, spread over time as each perturbed orbit completes enough of its revolution to bring it close to the Sun. The models differ on the total numbers, ranging widely depending on the density and off cloud and the precise geometry of the approach. But even the conservative estimates describe an encounter producing a shower unlike anything in the solar system's recent history, with many millions of new long-period comets sent toward the inner system over the span of millions of years following the closest approach. The shower would not look like a sudden bombardment from the inner system. It would manifest as an elevated background rate of new comets arriving more frequently than normal and persisting for a very long time before subsiding. Jupiter and Saturn stand between that rain and the inner planets. As they always have, the giant planets gravitationally deflect a large fraction of the comets that enter the inner system, bending their paths, absorbing some, sending others back out on trajectories that escape the solar system entirely. The shower that reaches Earth-crossing orbits is a smaller fraction of the total than what leaves the cloud. The giants do not provide a complete shield, and some elevated fraction of comets during the shower would come close to the terrestrial planets. The probability of any individual comet striking Earth remains low. Over millions of years of increased flux, the total probability of an encounter is what the models try to quantify with considerable uncertainty. The precision is what catches me here. Gliese 710's arrival time, 1.25 to 1.33 million years from now, is a number we hold with more confidence than most things people ordinarily call certain. It is 250 times the entire span of recorded human history. No civilization, no language, no institution has ever persisted for even a fraction of that time. And yet we have calculated. From the current motion of a point of light 64 light-years away, the approximate shape of an event that will unfold long after everything we have ever built has been replaced by something unrecognizable. The precision and the futility exist at the same scale. We know it is coming. We will never be there to see it. Both of those things are simply true at the same time, which opens the final part of the question. Gliese 710 is the one we have measured. It is not the only star that has ever made this approach. In 4.5 billion years, the outer cloud has been crossed by dozens of stars at various distances, some of them closer than what Gliese 710 will achieve, some of them sending comet showers into the inner system during eras when the Earth already had oceans and continents and life evolving on its surface. Did any of those showers reach the ground? And if they did life on Earth carry the mark of it? The clearest case we have is 66 million years ago. A large body from space, somewhere around 10 kilometers across, struck what is now the Yucatan Peninsula in Mexico, and released energy so far beyond ordinary geological experience that the comparison is almost absurd. The sky filled with debris. Fires ignited globally. Dust and soot blocked sunlight for years, and the collapse of photosynthesis cascaded through food webs that had taken hundreds of millions of years to build. By the time the climate stabilized, roughly 3/4 of all species on Earth were gone, the non-avian dinosaurs among them. That event is about as well established as any in the deep history of life, not because of fossils alone, but because the impact left a chemical signature in rocks worldwide, a sharp layer of iridium and other platinum group elements deposited simultaneously across every continent we have examined, and a crater the size of a small country buried under the Yucatan. What makes it a powerful anchor for the sky and life question is not just the scale of the extinction, but the clarity of the cause. A single, identifiable, astronomical event produced a measurable, global, near-simultaneous signal in the geological record. We can date it, map it, and read its chemistry. Most extinctions do not leave that kind of evidence. Most extinctions are slow, spread over millions of years, produced by some combination of volcanism, atmospheric change, sea level shifts, and biological pressures, with any cosmic contribution blended into the noise. The end Cretaceous stands apart because one moment left a visible line in the rock, and everything below that line lived, and everything above it had to start over. The complicating fact is that the Chicxulub impactor was most likely not from the Oort Cloud. The chemical signature in the iridium layer points to a type of stony asteroid, a carbonaceous chondrite, of the kind that forms in the outer asteroid belt rather than in the icy outer cloud. Comets from the Oort Cloud are primarily composed of ice and dust, and their chemical signature would differ. The body that ended the Cretaceous was probably a rocky wanderer from the belt, sent onto a planet-crossing orbit by gravitational interactions with Jupiter over millions of years, not a comet recently nudged inward by a stellar encounter. The clearest connection between a cosmic event and a mass extinction does not, on current evidence, implicate the cloud. The deeper question is whether the Oort cloud has contributed to extinction events in more diffuse ways, over longer timescales. Not a single specific impact traceable to a single source, but an elevated background rate of cometary impacts spread across millions of years of a comet shower, statistically increasing the probability of large bodies reaching Earth during periods when the cloud was disturbed. This is the version of the question that involves the stellar encounters we traced, and it is substantially harder to answer. In the early 1980s, two paleontologists examined the marine fossil record and found what appeared to be a rhythm. David Raup and Jack Sepkoski analyzed extinctions over the past 250 million years and reported a pattern repeating roughly every 26 million years. The extinctions were not all of equal severity, but the timing seemed non-random, and a 26 million year cycle was striking enough to ask what was driving it. Several cosmic mechanisms were proposed, among them a hypothetical companion star to the Sun orbiting far enough out to periodically disturb the Oort cloud on that timescale. If an astronomical clock were producing periodic comet showers, and if those showers were producing periodic extinctions, the sky and the fossil record would be connected in a very direct way. When other researchers examined the claim, the picture became less clear. Some analyses found the periodicity robust, others found it marginal or absent, depending on which fossil database was used and which statistical methods were applied. The proposed mechanisms produced contradictions. The galactic plane oscillation that some researchers cited generates a timescale of roughly 30 to 35 million years in most models, not quite matching the 26 million year claim. No companion star was found, no distant planet confirmed. The current state of the hypothesis is unresolved at best, and most researchers treat it as an interesting idea that has not been established, rather than a settled piece of the picture. The difficulty is not unique to this particular hypothesis. It runs through every attempt to connect astronomical events to biological ones over geological timescales. Think of trying to trace the footprints of a specific storm on a road that many storms have crossed over millions of years. The individual prints are gone. What you have is the current state of the road, eroded and resurfaced and eroded again, and a general record of how much weather the region has received. From that you might conclude that storms happened. You cannot conclude which storm left which mark. Extinctions work the same way. Each one has multiple candidate causes, and distinguishing a comet shower's contribution from the contributions of volcanism, climate change, or ecological collapse requires a precision that the geological record, at timescales of tens of millions of years, rarely provides. The signal we are looking for is real in principle. The road has simply been crossed by too many other things for us to read it clearly. Whatever the contribution of stellar encounters to the history of life on Earth, the biology that produced you has been running continuously for longer than the cloud has been orbiting in its current form. The same orbital mechanics that will reshape the cloud after Gliese's 710 passes have been operating since before the first cell divided on this planet. Every extinction that cleared a path, every survival that continued a lineage, every comet that may or may not have fallen during a period of elevated flux, all of it is part of the unbroken sequence that produced the particular arrangement of biology that includes this conversation, this night, and the fact that you are here at all. Not as a story of cosmic purpose, as a plain statement of continuity. The cloud is not separate from the history of life on this planet. It is one of the forces that has been running on the same timescale, shaping the same world. Across all of this, the tides and the encounters and the showers and the 4.5 billion years of orbiting, there is one question we have not yet asked directly. Not what has come in from outside, and not what has been stripped away, but what we have sent out, how far our own messengers have traveled, and whether they have crossed any of the territory we have been describing. or whether they are still, even now, only just beginning that crossing. There is one object we can locate precisely in this moment, whose speed we have measured, whose position we know to the kilometer. How far has it gone? And what waits between it and the edge we have spent so long tracing? The answer to the first question is around 170 astronomical units from the Sun. Voyager 1, launched in September of 1977, has been moving outward ever since, past Jupiter, past Saturn, past Uranus, past Neptune, past Pluto, past the edge of the heliosphere where the solar wind gives out and interstellar plasma begins. It crossed into that interstellar medium in 2012, and it has been there ever since. In that narrow sense, it has already left the Sun's atmospheric domain, the bubble of charged particles the Sun continuously exhales into space, but the gravitational domain, the cloud, the territory we have been mapping, extends more than 10 times farther. The wind is not the territory. The territory is everything the Sun can hold in orbit, and Voyager has barely begun the crossing. Place that number against the territory we have been crossing. If the distance from the Sun to Neptune fits in a single step, the inner fringe of the Oort cloud begins roughly 60 steps away, and the outer edge of the cloud lies more than 3,000 steps beyond that. Voyager, at about 5.5 steps out, has not yet taken the first full step toward the cloud. It is between the door and the gate, having left the house but not yet entered the yard, in a solar system where the yard is where most of the property actually is. Moving at roughly 61,000 kilometers an hour, about 38,000 miles an hour, Voyager covers more ground in a single hour than 13 times the width of North America. In a single day, it travels nearly 4 times the distance from the Earth to the Moon. That is roughly 60% of the speed the Earth moves in its annual orbit, sustained for nearly 50 years without any fuel speed. It acquired from the gravitational slingshots of the giant planets in the 1970s and has never lost. By any standard that fits inside a human life, it is moving very fast. By the standard of what it is trying to cross, it is barely moving at all. The time required to cross the cloud runs like this. In a few centuries, not long by the clock we have been keeping in this journey, but centuries after the last person with any living connection to its launch is gone, Voyager will enter the distances where the innermost fringes of the cloud region begin. In the first few thousand years of that passage, it will drift through the inner reservoir, the denser shell that the galactic tide has been sculpting since before the first animal drew breath on this planet. In tens of thousands of years, it will be in the outer cloud. In roughly 30,000 years, it will have crossed the full extent and emerged beyond. 30,000 years ago was the height of the last ice age. The oldest cave paintings in Europe were being made. No human had yet set foot in the Americas. Everything in recorded history, every civilization, every document ever written, fits inside a window 1/6 the length of that single crossing. Long before any of that crossing begins, the probe will go silent. Voyager 1 runs on the slow decay of plutonium, and the power has been fading since launch in a process that never stops and cannot be reversed. Within the next few years, it will no longer generate enough power to run any science instrument. Within a decade at most, the signal will fall below what any receiver on Earth can detect. The last transmission will go out, and there will be no reply and no way to confirm it arrived, and then the link will be closed. After that, Voyager becomes what it will remain for the next 30,000 years. A metal object no larger than a small car, dark, cold, moving at 38,000 miles an hour through the most remote region of the solar system, carrying nothing that still functions. No instrument it carried was designed to detect the individual icy bodies of the cloud at those densities. And by the time it enters the cloud, there will be no power to run anything anyway. The objects it drifts near, if it drifts near any at all, given how sparsely populated even the densest region is, will be dark and cold and separated by tens of millions of miles of nothing. The probability of any actual collision is vanishingly small. It will pass through the full population of the cloud we have been tracing and most likely never touch a single one of its members. Moving through it, not knowing it is there, what it carries, even in silence, is a direction. The course Voyager 1 follows was plotted by human beings in the 1970s, using centuries of accumulated mathematics to slingshot the probe around the giant planets and send it outward on the precise path it now travels. That calculation is not stored in any circuit that will still be running. It is not in any memory that survives. It is encoded in the physics of the trajectory itself, in the velocity and angle that were imparted to a metal object and that the laws of motion will preserve indefinitely. An object moving through a gravitational field with a specific velocity and direction carries that information forward as long as it continues to move. Voyager's path is not a transmission. It is a message written in momentum. It does not need power. It simply continues. What that transition carries, the last signal, and the code that follows, is not diminishment. It is the plainest statement of what reaching out means at these scales. We built something. We calculated a path. We sent it out with everything we knew. The path is still running. Whatever we were asking when we launched it, whatever the question was that made it worth building and sending the question, is still traveling, still heading toward the edge we have spent so long tracing, still moving at 61,000 kilometers an hour, through a desert so wide that even at that speed, nothing built by human hands will cross it within any time frame that has a name in any human language. The curiosity is still out there. It is just running in the dark. When the signal goes quiet and the probe keeps moving for centuries and then millennia and then the full 30,000 years of the crossing, it is doing what the cloud itself does. It persists. It drifts. It carries a history in its momentum that nothing can erase without stopping it entirely. And the cloud it is crossing has its own outer limit, the place where the sun's authority finally gives way to the galaxy. We have been approaching that limit from many directions at once. Now we can ask directly where the edge actually is, and what, if anything, waits on the other side. The outer edge has a name in the physics. It is called the tidal truncation radius, and it marks the distance at which the galactic tide becomes strong enough to unbind anything the sun tries to hold there. Not strong enough to pull objects inward, the tide does not direct things toward the sun or away from it. Strong enough to disturb any attempt by the sun to keep an object in a stable, closed orbit. Past this radius, a body may orbit loosely for a while, but the tide will gradually reshape that orbit until the object drifts free. The sun cannot maintain its cloud of ice beyond this threshold. This threshold is the edge. What the threshold looks like in practice is not a wall, but a slow handover. Inside the truncation radius, orbits can close, precess, and survive for billions of years. Outside it, orbits open over time, and the objects on them drift gradually toward interstellar space. The transition is not sharp. Objects near the threshold oscillate between bound and unbound as the tide and the sun's gravity push against each other over millions of years. The material at the very outer fringe is the most provisional of all, neither firmly held nor definitively lost, existing in a slow negotiation between the sun and the rest of the galaxy. The distance that results from this negotiation sits somewhere between 100,000 and 200,000 astronomical units, or roughly 1.5 to 3 light years. That number carries some uncertainty because the galactic tide is not perfectly uniform and the sun's position within the galaxy has shifted over its lifetime. But the range is well constrained. The nearest star, Proxima Centauri, lies about 4.25 light years away. The sun's gravitational territory, at its outermost extent, reaches somewhere between 1/3 and 3/4 of the way to its nearest neighbor before the galaxy takes over. The edge of everything the sun calls its own falls somewhere in the long, dark middle between two stars. Think of two streetlights placed far apart on a very long, dark road. Each casts a glow that spreads and fades with distance. Near each lamp, the light is strong and clear, Moving toward the midpoint between them, each lamp grows fainter, and at some point along the road neither is clearly brighter than the other. The space between the two pools of light is not dark. It is lit by both at once, weakly. There is no line you could draw on the road and say, here the first lamp ends and here the second begins. There is only a fading, then an overlap, then a strengthening of the other. Return that image to the physics, replace the lamps with stars, the light with gravitational influence, and the road with interstellar space. At the midpoint between two stellar systems is not emptiness, but a place where both suns are pulling with roughly equal weakness, and where anything sitting there belongs, in the minimal sense, to whichever of the two is exerting slightly more pull at that particular moment. If Proxima Centauri has its own cloud extending to a similar distance, the outer fringe of our cloud and the outer fringe of Proxima's cloud may already be close to each other, possibly overlapping in the space between the two stars. Not physically overlapping in any dramatic sense, the densities are too low for the objects of one cloud to meaningfully encounter the objects of another. But gravitationally, the influence of both stars at those distances would be present simultaneously, both weak, both unable to claim the objects in the overlap region with any certainty. The territory between stellar systems, which we have always imagined as a void, a true gap, may instead be a region where two fading authorities share an uncertain jurisdiction, not no man's land, shared land so weakly claimed that neither star could hold anything there against the mildest perturbation. For a time, some researchers proposed that the outer structure of the cloud might be shaped by a large hidden planet, something the mass of Jupiter or Saturn, orbiting the Sun at tens of thousands of astronomical units, its gravity sculpting the outer shell and causing long-period comets to arrive from preferred directions in the sky. This hypothetical planet was named Tyche, after a figure from Greek mythology associated with fortune. The proposal drew on observations that appeared to show clustering of long-period comet aphelia, the farthest points of their orbits in one region of the sky, a pattern that would be consistent with a large nearby mass pulling on the cloud from one direction. Philip Matisse and Daniel Whitmire developed the proposal in detail and published it. It was a serious scientific hypothesis, not speculation, and it deserved investigation. An infrared survey of the sky, completed in the early 2010s, covered the distances and temperatures at which an object of the proposed mass would have been detectable by its own heat radiation. A body the mass of Jupiter orbiting anywhere inside the inner cloud distances would have appeared. Nothing appeared. The survey did not rule out smaller or colder objects. Surprises in the outer solar system remain possible, but the specific Tyche hypothesis, as originally proposed, has not survived the test. The clustering of comet aphelia that motivated it has also been reanalyzed and found to be less significant than originally reported. The outer edge of the solar system, for now, does not appear to have a hidden architect. Whatever structure the outer cloud carries was built by the forces we have already traced. I spent a long time looking for the edge of this system before I understood that the question carries at least 4 different answers. The heliosphere ends at roughly 120 astronomical units, where the solar wind gives out. The planetary region ends around 30, where Neptune traces the last visible circle. The Hills cloud begins at 2,000 and runs to 20,000. The outer cloud extends to 100,000 and beyond, and the tidal truncation radius sits further still. Each of those limits is physically real. Each answers a different question about the solar system. The reason we tend to collapse them into a single phrase, the edge, is not because there is one edge, but because we needed one word before we knew how to distinguish what we were actually asking. What that compressed word did was make the system feel smaller and more certain than it is. The precision was always there. The vocabulary was catching up. The sun's authority fades across all of those distances, from the grip that holds Neptune in a nearly circular orbit to the whisper that can barely keep a distant piece of ice from drifting off into the galaxy. At the very outer limit, what remains of that authority is barely distinguishable from the background pull of everything else. The territory does not end, it dissolves. And the same physics that produces that fading, the same gravity and orbital mechanics we have followed from the cloud down to the ocean tide, has been running in everything we are all along, in this room, in this body, tonight. What any of this looks like, finally, from inside. From inside, it looks like water. It looks like calcium and iron and carbon. It looks like trace amounts of elements that required a supernova to make. It looks like a collection of atoms that did not originate in this solar system, that have traveled through more history than any object in the Oort Cloud, and that are assembled right now, in this room, into a temporary arrangement that is aware of itself and curious about where it came from. Start with the water. About 60% of your body by mass is water. Each molecule of water is 2 hydrogen atoms and 1 oxygen atom. The hydrogen was not made in any star. It was made in the first few minutes after the universe began, roughly 14 billion years ago, in a period of heat and density that no star or planet was alive to see. The hydrogen in you is among the oldest matter in the universe. The oxygen is younger but still ancient, forged in the cores of massive stars that lived fast and died in explosions that scattered their contents across space. Those explosions happened before the sun existed. The oxygen entered the collapsing nebula that eventually became the sun and its planets and its cloud, already old, already carrying the chemistry of the stars that made it. The same is true of the rest of you. The calcium in your bones was forged in stellar interiors and distributed through supernova explosions over billions of years before anything on Earth had bones to use it. The iron that carries oxygen through your blood is made only in the cores of the most massive stars and released only when those stars end catastrophically and seed the surrounding space with the heaviest elements. Every iron atom in your blood came from a dying star. The carbon in your DNA, the phosphorus in your cell membranes, the nitrogen woven through every protein your body has ever assembled, each of these has a history measured in billions of years and distances measured in light years. You are not made of local Earth material that has stayed close to home. You are made of the galaxy's material, organized into a temporary pattern by the chemistry of one small planet. And you are not holding on to these atoms permanently. Different parts of the body turn over at different rates. Much of the water in you will have cycled through in days or weeks. The atoms in your skeleton are replaced over years. By some estimates, the atoms that compose you today are not the same atoms that composed you a decade ago in most of the cells that matter. You are not a fixed inventory of specific particles. You are a pattern, a way of organizing matter that has been maintaining itself through a continuous flow of material borrowed from the world and eventually returned to it. That is not a reduction. It says that what persists is not the specific collection of atoms, but the way they are organized, and that the organizing principle, whatever makes you recognizably you across decades of cellular turnover, is something no individual atom carries alone. The same thing that is true of the Oort Cloud, material cycling in and out while the structure persists, is true of the body that followed this journey tonight. The moon is raising a tide in you right now. We traced that long ago, the same differential gravity that peels comets from the cloud acting on the water in your cells at this moment, too gently to feel, but real and continuous. The galactic tide that sculpts the outer cloud is acting on your atoms as well, at a scale so far below any threshold of sensation that no instrument built into biology could register it. And yet the equations that govern both are the same equations. The force that shaped the spiral structure of the inner cloud and the force nudging your atoms through space tonight are the same kind of force, wearing different magnitudes. What you will not find, if you look carefully enough, is a sharp edge where you end and the universe begins. At the surface of your skin, atoms are leaving with every breath. Every molecule of water vapor exhaled into the air around you. Others arrive. Atoms of oxygen taken in. Atoms of food metabolized. Atoms of everything you have touched that has become part of your chemistry. The boundary of a body, at sufficient resolution, is a gradient. a region where the organization characteristic of you fades into the organization characteristic of everything else. The same kind of fading we found at the outer edge of the solar system. The same kind of dissolving boundary. The same answer to the question of where something ends. Home, then, is what this entire journey has been trying to define, and the physics gives the same answer at every scale. Home is not a point with a fixed edge. It is a pattern of organization, persisting through exchange, maintaining its character through the continuous cycling of material that passes through it. The sun's home is everything it can hold in its gravitational basin, through gradients that fade to whispers at the outer cloud. Your body's home is the pattern it maintains through borrowed atoms, temporarily organized, always in flux. The Oort Cloud carries the same mixture of origins we carry, material from multiple stellar sources, held together by a common gravitational history. We mapped that mixture from the outside, across light years of cold and dark. It turns out to be the same story as the inside, told at a different scale. Every atom you used to follow this tonight has been part of that same long history. The supernovae, the nebulae, the solar disk, the cloud we traced from the classroom map all the way out to the place where the sun's authority dissolves into the galaxy. You did not travel out to meet the universe. It has been cycling through you the whole time, in the very matter you are using to think about it. That is the whole journey. We started with a classroom map that stopped too soon and ended here, with the physics of the Oort Cloud running in the same atoms that made it possible to ask where the Oort Cloud is. There is something settling in that, not because it makes us large or important, but because it means the curiosity is not separate from what it is curious about. The wondering and the wondered at are made of the same thing. It is late now, and you have thought about very large things for a long time. The dark around you is the same dark we traced all the way out to the tidal truncation radius and back. Nothing changed. It was always this dark, and always this close, and it was always full of this. Sleep well. Thank you for coming all this way with me. It has been a real pleasure to think through all of it alongside you.